Namaskar friends, welcome to session 36 in our course on processing of polymers and polymer composites. In the last session we were discussing the secondary processing of composites, that is polymer matrix composite materials, and if you remember what we have covered in the previous session, you may be remembering that we have covered that what are the different types of damage that takes place during the drilling of polymer matrix composites. And we have seen one summarized slide in which we have tried to cover that what are the methodologies adopted, what are the techniques adopted in order to minimize the drilling induced damage. Again I am emphasizing the importance of minimization. Till today, if you have a composite material, suppose you have a natural fiber reinforced polymer composites, suppose you use a bagasse fiber with a polypropylene matrix, you make a composite material. I believe that none of the researchers will be able to tell you that you should make a hole using this drill at this cutting speed and at this feed rate. That is the complexity of the problem. As the material changes, your conditions also change. Your cutting speed or the optimal cutting speed will change. Your optimal feed rate will change. Your optimal tool material will change. Your optimal tool point geometry will change. So as soon as you change the fiber, as soon as you change the matrix, your conditions automatically change. Therefore, making of holes in composite materials is a difficult task. But the overall problems remains the same. In the last session, we have seen that there is damage that takes place around the hole, and that is the biggest challenge. And we have seen that we may get a peel up type of delamination, we may get a push down type of delamination. Now this delamination has to be controlled. We may get a circularity defect around the hole, we may not get a exactly circular hole, we may get out of roundness, we may get poor surface roughness around the whole wall. So all these things we need to control. And how we can control all these types of damage? We have seen that number of strategies have been adopted worldwide in order to minimize this type of damage. And today also we are going to see that what process modifications we can do in order to make holes that are of good quality. So I am not clarifying, or I am not establishing, or I am not claiming that we will be able to make a clean cut good quality hole using any one of these techniques. But yes, these techniques have certainly resulted in making holes which are better in quality as compared to the standard approach of conventional hole making that usually we call as the drilling of polymer composites. So today we will focus on slightly modifications or slightly modified methods of making holes in polymer composites. So let us start our discussion by just having a brief review of the methods that have been used for avoiding the damage. So let us see our first slide. That is, first thing that we have covered in the previous session was how to avoid the damage. Now that we have already covered in the previous session, just I will not explain each point in detail, but we will just like to revise that what are the various methods, techniques, tools to avoid the damage. The first is the selection of the optimal operating variables, that is the cutting speed and the feed rate. If we select them properly, our damage will be less. Tool material also we need to select a tool material which will give us good surface finish around the hole. Tool point geometry I have shown in the previous slide, in the previous session. Towards the end of our session, if you remember, we have seen the thrust force signal varying with time, we have seen the torque signal varying with time, and these signals will change with respect to the tool point geometry. So the tool point geometry selection is also very important, because the tool geometry will influence the forces will subsequently influence the damage. So we have to be very judicious in selection of the tool point geometry. Selection of the appropriate process. Today we will see that what are the modifications in the conventional drilling process which have been adopted worldwide and which have resulted to minimizing the effect of damage in the holes. Then the dedicated machine tool, we have seen that the machines that we use for making holes in metals may not be that applicable for making of holes in composite. So we have to design, develop machines which are specific to the concept or specific to the composite materials. Finally, we have to intelligently select the cutting fluid which may act as a coolant, which may also act as a lubricant. Then finally, the last thing, that is the improvisation, the innovation in the machining processes which can lead to minimization of the damage. And that innovation and improvisation, the examples are the woodpecker cycle, the use of the backing up plate, and these are the 2-3 techniques that we are going to cover today. And we will see that these techniques have definitely led to improvement in the quality of the hole in case of drilling of polymer composites. So the first method to avoid the damage is the appropriate selection of the tool point geometry. Prior to that, we need to judiciously select our cutting speed, we need to select the feed rate. So those are the two important things. Apart from that, what we can control is the tool point geometry. And here this slide has already been shown in the previous session also, but again I am emphasizing this slide again. You can see this is the twist drill, saw drill, candlestick drill, core drill, step drill. So different types of tool point geometries can be used for making holes in different types of composite materials. Must I mention that there was a research article published in American Machinist in the year 1987, published by Joseph Miller, J.A. Miller, and there in 1987 itself he investigated 17 different drill point geometries, and he proved that the drill point geometry plays a pivotal role, plays a paramount role in defining the damage around the drilled hole. And here we are just showing only 5 different geometries which have been used, and you can yourself see the central portion. Again I am emphasizing is the actual hole that we want to make, and around the hole you see the damage. And for twist drill, which is the most commonly used drill for making holes in metals, results in the maximum damage around the hole, whereas the modified drill point geometries, that is the saw drill, the candlestick drill, the core drill or the step drill, all these drills are leading to lower damage or lower drilling induced damage or minimum drilling induced damage around the hole. So here twist drill leads to maximum damage, and maybe in this, if I have to visually examine, I may say that the core drill is leading to the minimum damage around the hole. But scientifically, if we find out or quantify the damage around the hole, there are number of tools and techniques. One of the best technique to quantify the damage around the drilled holes can be the non-destructive dye penetrant testing. Then we can use a ultrasonic C scan also to see the area or observe the area around the drilled hole. So here just by visual examination I can suggest that twist drill leads to maximum damage and the core drill is leading to the minimum damage. So which establishes the importance of tool point geometry as an important criteria for defining the damage around the drilled holes, and that is why we should appropriately, judiciously, optimally, intelligently select the drill point geometry so that the damage that we get around the drilled hole in case of polymer matrix composites is minimum. So this is one of the important factors to be taken into account to minimize the damage. Then we can see the modified drill point geometry. This is further modification. Here you can see there is a through coolant hole here. These are the two holes. So the twist drill with an arrangement of coolant flow at the cutting zone. So different types of tool geometries can be investigated for optimizing the drilling performance of the polymer composites, and this can be one drill. As I have discussed in the previous session also, that it is always not important to use the coolant or the lubricant or the cutting fluid in case of composite materials. Why? The reasons I have explained in the previous session also. There can be maybe a reaction between the polymer and the lubricant or the cutting fluid which may be detrimental to the performance of the composite part with the drilled hole during the in-service condition. So that needs to be taken into account, that in all cases we may not like to use the cutting fluid, but yes, in specific cases where cutting fluid is going to give us good performance, a modified drill point geometry that as shown on your screen can be helpful in improving the drilling performance during drilling of polymer matrix composites. Similarly, we can see the other drill point geometries which have been investigated. This is an article by M. Ramulu, P. Yong and H. Cow. You can see the article was published in 1999, that is maybe 18 years before, and they have investigated 3 different drill point geometries, and the names goes like this: step core twist drill, step core saw drill, step core candlestick drill. So different types of geometries have been tried in order to avoid the damage in the damage around the hole in case of polymer matrix composites, and more specifically fiber reinforced plastics. So by now I think all of you, all the learners, all the students who are attending this course may be able to emphasize on the importance of drill point geometry as an important criteria in defining the drilling performance in case of polymer matrix composites. Now we will shift our attention slightly towards the processes that, or the process modifications that can be done in order to minimize the damage. Now there are advanced techniques of hole making in polymer matrix composites. So these are modifications in the conventional method only. Advanced techniques, usually when we talk of advanced machining or advanced manufacturing method, usually we go to the unconventional methods of machining. If you ask somebody what are the advanced machining method, prompt is the reply that electric discharge machining, ultrasonic machining, electrochemical machining, plasma arc machining. So here these processes are not advanced, or these are not unconventional. These are the modifications in the standard techniques only. That is, standard drilling operation is that you have a spindle, you have a drill mounted on the spindle, there is a fixture, you mount your workpiece there and you make a hole. This is the conventional hole making approach. So the processes that we are going to cover today, maybe 2 or 3 processes we will cover, will be the modifications of the conventional drilling method, and subsequently we will shift our attention towards the non-conventional hole making techniques also, specially applied to hole making in polymer matrix composites. So let us quickly first look at the woodpecker cycle. Now all of us have seen a woodpecker bird, even if we have not seen on our television sets or maybe on internet, we may have seen that, or we may have observed that how a woodpecker makes a hole in the tree. Now the same concept can be used for making holes in composite materials. Now here you can see peck drilling simulates the action of a woodpecker bird, and the woodpecker bird, how it makes a hole, we will try to understand it with the help of a diagram, but the woodpecker cycle helps us to have better productivity. Now productivity will be better if the damage around the hole is less, and we are able to make more holes with better quality with minimum damage, or try to minimize the rejection rate. If you remember, in last to last session I have emphasized that the rejection rate is to the tune of 50% in case of drilling of polymer matrix composites. So if by choosing a modified method of hole making we are able to reduce this rejection rate, that will always lead to the higher productivity. So the productivity can be better if we use the peck drilling method, then better chip evacuation or better chip removal can be achieved using the peck drilling or the woodpecker drilling cycle. So let us try to understand what is this method. Now on your screen there is one diagram which explains the different stages of a peck drilling or woodpecker drilling cycle. So this is our spindle, it shows the rotation, and this orange color represents our drill. At the start of the drilling cycle, the drill enters into the laminate and then it is retracted back. Again it goes to the certain depth and again it is retracted back. Then it goes to the full depth and then it is retracted back. So in each retraction the chips are also removed. So we are doing the drilling in 3 stages now. The first stage is up to a particular depth, and then the drill is retracted back, and then up to a intermediate depth, again the drill is retracted back, and finally we go to the complete depth of the hole, and finally the drill is retracted back. So after each drilling cycle, retract the drill out from the hole to ensure that no chips are stuck onto the drill. So this process leads to better chip evacuation of the chip removal. Now some of you may be wondering how this process can be better than the conventional drilling method, because in conventional drilling the drill will come in contact with the workpiece and then continuously it will move down and it will complete the hole and come out or exit from the other side if it is a through hole. And in that case the time taken will be less as compared to the woodpecker cycle, because it is a single go process, and here we are going 3 times to make a hole of the equivalent depth. Now that is a very valid question, that how this process is better than the conventional drilling process. In conventional drilling process, in most of the machines that we use, we have a constant feed rate. And when you have a constant feed rate, in the beginning, suppose I want to make a hole in a 10 millimeter thick plate or a 10 millimeter thick composite laminate. As soon as I start to make a hole from the top, I have fixed a feed rate. For example, it is 0.3 millimeter per revolution. Now at this feed rate, constant feed rate, I am going down and I am generating a hole in the composite laminate. Now the feed rate remains constant till the end I have made the hole, but the material that is under the drill keeps on reducing as and when the drill is moving down. So towards the end of the hole making operation, the material that is just below the drill before being cut, the thickness reduces continuously, and therefore the thrust force towards the end of the hole making operation will lead to the delamination of the bottom layers, and that constant feed rate is therefore become a challenge. Here in this case, we can even manipulate the feed rate towards the last cycle. Towards the last entry of the drill, we can manipulate, we can change our feed rate. In conventional drilling also these days CNC machines are available in which we can write a program and we can maneuver, we can manipulate our feed rate during the cycle or during the drilling cycle also. But maybe 15, 20, 30 years back, the constant feed rate machines were most widely used, and therefore there was this problem. But today we can program the machine in such a way that the feed rate follows a particular trajectory or the feed rate follows a particular cycle, so that towards the end the feed rate is less. In the beginning we have a high feed rate and towards the end we can have a low feed rate, so that we are able to minimize the effect of push down type of delamination. But in this case the push down delamination will certainly be less as compared to the conventional drilling if we are using a constant feed rate setup or constant feed rate machine tool. What can be the advantages of this woodpecker method? I will quickly read out the advantages. I have already explained: better productivity, low drill breakage, better chip evacuation, decrease in the thrust force, decrease in the drilling temperature, and decrease in the drilling induced delamination. Out of all, if you ask me to choose one, I will definitely pick the last one, that is the decrease in the drilling induced delamination. That the damage that occurs around the hole is minimized if you use a woodpecker type of cycle as compared to the conventional drilling technique or conventional drilling method. Let us now see the use of the backup plate. On your screen there is a very simple diagram. This is a drill, not exactly representing a drill, but okay, we can say it is a drill tool or a cutting tool. A rotation is shown, it is rotating, and then it is making a hole. This is the complete, the capital T is giving us the overall thickness of the laminate, and the small t is representing the uncut thickness of the laminate. Now this red color portion has been highlighted here. This red color plate is our backing plate. Now if you have seen, or if you remember, in the previous session I have shown the push down type of delamination. Now push down type of delamination occurs towards the end of the laminate or towards the bottom layers of the laminate when the drill just exits from the hole. Now in this case, when you put a backing up plate below the laminate, the lower laminae will not get a chance to delaminate because they are supported from below with the help of a backing plate, and that support will not allow the debonding of the bottom layers under the effect of thrust force. And so this backing up plate will help us to reduce the effect of push down type of delamination, and this has proved successful in reducing the effect of push down type of delamination. Now some of you may be wondering, when this technique has already been developed, it has been found to be successful, then why still people are conducting research in order to avoid or in order to minimize the push down type of delamination? The question is very valid. It is true that this technique will help us to minimize the effect of push down type of delamination, but in many situations, in many applications, it is very difficult to place a backup plate in the exact location where the hole has to be made. So in that situations where you cannot have a backup plate, you need to develop techniques, you need to develop methods which can help you avoid the drilling induced delamination without the use of the backup plate. So therefore this is possible, this is helpful, but in specific application areas only, and there are other areas where this backup type of plate will also not be that useful. But this is one method, if possible, we can use to avoid the push down type of delamination. Now what can be the advantages of the backup plate method? So decrease in the drilling induced damage. So that I have already told. Drilling induced damage, we are currently focusing on two important types of damage only, that is the peel up type of delamination and the push down type of delamination. So this particular type of backup plate, which is just placed just at the bottom of our laminate during the drilling operation, will help us avoid the push down type of delamination, and the quality of the hole produced is also very good. Next method that we can use to reduce the damage is the helical feed method. In helical feed method, our drill will not go down along the axis of the drill, but it will revolve around the axis of the hole. So if we will try to understand it, I will try to explain it with the help of a diagram. So here you can see on your screen, we want to make a circular hole. So the drill is not moving down, or the cutting tool is, or the twist drill is not moving down along its axis, but it is moving down just in the helical method. So the feed is given helically so that the drill just also rotates and it moves down helically, it does not move down straight. So you can see a helical feed drilling method, it improves the drilling performance over the conventional drilling. How it improves? What is the difference? That has been clearly outlined in second point. The difference between the two methods. What are the two methods? The conventional method and the helical feed method. So the difference between the two methods is that the drill in helical feed method moves down helically with respect to the drilling axis. So it does not move down straight, whereas in case of conventional drilling, it moves down straight along the axis. Now helically, when it moves down, the thrust force is reduced, and when the thrust force is reduced, your push down delamination is definitely going to reduce. But the challenge is that you need to modify your machine tool accordingly. And if you remember, we have already covered in our title slide how to avoid damage, that we need to develop dedicated machine tools for avoiding this damage. And dedicated machine tool means that we need to modify sometimes our machine tool. In most of the drilling machines or drilling machine tools, we have a constant movement of the drill. Feed rates are also almost constant, and the drill moves along its axis down into the workpiece material. But in this case, the drill has to move in a helical way, just not along its axis, and therefore a dedicated machine is required for this purpose. But certainly it has been proved, it has been experimentally validated, it has been experimentally established that if you use a helical feed method of feeding the drill into the workpiece, it leads to less thrust force and helps us to avoid the drilling induced delamination, specifically the push down type of delamination. Now what can be the advantages of the helical feed method? Chip removal is better because the chips get more space to come out from the hole area. Flow of the coolant is better. It can be very easily understood if you just focus on the diagram, which a very schematic diagram that we have shown today, very simple schematic. You can see that more area for the coolant to flow down. As I have already explained, decrease in the thrust force, that is but obvious, decrease in the drilling induced damage. So when the force will decrease, subsequently in almost 99% cases your damage will also be less. Quality of the hole produced is good and the temperature produced is less. So the matrix burning is less and there is less temperature or heat buildup in the machining zone during the drilling of the polymer matrix composites. So with this, I think we conclude today's session, and we have seen today that drilling induced damage is a very big problem. It is an important issue. We need to avoid the drilling induced damage, and we have seen that there are three important methods which can be used for minimizing the effect of drilling induced damage in case of polymer matrix composites. Now what are these three methods? We have seen that we can use a helical feed method. We have seen that we can place a backup plate just below the composite laminate during the drilling operation, and the first method that we have seen that we can use a woodpecker cycle in order to avoid the drilling induced damage. So all these three methods, the woodpecker cycle method, the backup plate method, the helical feed method, all these are modifications in our conventional drilling methodology, and these modifications have specifically helped us in order to make or in order to minimize drilling induced damage in case of polymer matrix composites. In our next session, we will focus our energy, we will focus our attention on understanding the unconventional routes or unconventional methods of making holes in composite materials, more specifically in polymer matrix composite materials. Thank you.